Hi guys, hello everyone. My name is Saurav and I'm a chemistry master teacher over here in Vedantu. Welcome to the VOS channel, and you know that we are conducting these short series of videos to help you understand certain interesting topics or certain difficult topics, certain challenging topics in chemistry at a much greater depth. So आज मैं आपके लिए the molecular orbital theory, which turns out to be one of the most interesting theories in chemical bonding, वो लेके आया हूँ. And molecular orbital theory को हम कुछ parts में करेंगे. पहला पार्ट जो होगा वो हम पहले समझें कि मॉलिक्यूलर ऑर्बिटल थ्योरी की ज़रूरत क्या थी, कंस्ट्रक्शन किस तरह से करते हैं, व्हाट आर द बेसिक फीचर्स, व्हाट आर द अगर एक मॉलिक्यूलर ऑर्बिटल थ्योरी को आप एक चेयर जैसा एज्यूम कर लो तो उसके पैर कौन कौन से हैं, व्हाट आर द थिंग्स इन ऑन विच इट रेस्ट्स, एंड on the basis of that we'll keep developing until we reach to understand how to construct molecular orbital diagrams. And believe me, we will try to form molecular orbital diagrams not in a very conventional way which is given in books, but in a slightly non-conventional way which will help you understand molecular orbital theory in a greater depth. उसके बाद हम पहुंचेंगे molecular orbital theory के applications के ऊपर. So अब ये जान के समझ लो कि मॉलिक्यूलर ऑर्बिटल थ्योरी जो है वो इतनी ब्यूटीफुल सी थ्योरी है, इतनी खूबसूरत सी थ्योरी है दैट मॉलिक्यूलर ऑर्बिटल थ्योरी कैन एक्सप्लेन ऑलमोस्ट not every, I would not say every, but a lot of behaviors, organic के कितने ही सारे reactions, कितने ही सारे outcomes, a lot of things in coordination compounds, a lot of things in spectroscopy, a lot of things in color, a lot of things in geometry, a lot of things in behavior of molecules. Somebody who's preparing for INChO or Olympiads, something known as pericyclic chemistry, इन सारी चीज़ों में molecular orbital theory का बहुत important role है, and the role is so very profound that you cannot ignore it. मतलब जब वैलेंस बॉन्ड थ्योरी आई थी तो हमें लगा था कि यार दिस इज द आंसर टू एवरीथिंग, बट ऐसा नहीं है. देयर आर लॉट ऑफ थिंग्स व्हिच वैलेंस बॉन्ड थ्योरी कैन नॉट एक्सप्लेन. सो चलो हम स्टार्ट करते हैं आज विद द आइडिया कि भाई हमें मॉलिक्यूलर ऑर्बिटल थ्योरी की जरूरत क्यों पड़ी. तो मॉलिक्यूलर ऑर्बिटल थ्योरी हमारे पास थोड़ा बाद में आया है. सबसे पहले तो हमारे पास वैलेंस बॉन्ड थ्योरी और वैलेंशियल इलेक्ट्रॉन पेयर रिपल्शन थ्योरी थे, और इनसे हमने काफ़ी कुछ आइडेंटिफाई. ऐसा मैं नहीं बोल रहा हूँ कि these theories are not important, but these theories have certain limitations. Every theory all of these theories have been very instrumental in helping us understand chemistry as we see it now, as we see it today. But the influence of molecular orbital theory is, I would say, groundbreaking. Okay, जैसे टेलीफोन काफ़ी समय से हमारे पास था, but since the time mobile phones and mobile networks have come, things have taken there is a huge change. उसी तरीके से molecular orbital theory केमिस्ट्री की दुनिया का सेलुलर डिवाइस है. ओके, सो वैलेंस बॉन्ड थ्योरी में यहाँ से स्टार्ट करते हैं कि वैलेंस बॉन्ड थ्योरी वाज स्लाइटली इनएडिक्वेट. ये इनएडिक्वेट क्यों था? मैं बहुत सारे एग्जाम्पल्स हैं, मैं आपको 2 एग्जाम्पल लेके सिखाता हूं. अगर मैंने कार्बन लिया, ये कार्बन है भाई साहब. कार्बन कंटेन्स how many electrons? So atomic number of carbon is 6, mass number is 12. Carbon contains 6 electrons, 1s2, 2s2, 2p2. अब इस तरह से इसका कन्फिग्रेशन लिखते हो. यूजिंग वैलेंस बॉन्ड थ्योरी अगर आपको बोला जाए कि भाई बताओ कि CH2 में CC बॉन्ड जो है, what is the nature of the bond that has been formed in this case? So what you will say is that this carbon is sp2 hybridized, and because it is sp2 hybridized, so this nature of bond that is between 2 carbon atoms over here is like this. There is overlap in this manner, and there is a sideways overlap that you will show. So you will show an overlap like this, and you will show overlap like this, and that you will suggest to form a sigma bond and a pi bond. ठीक है, आप इसको बोल दोगे पाई एंड इसको बोल दोगे सिग्मा. ठीक है, अब सेम आइडिया अगर मैंने इस मॉलिक्यूल C2 पे मैं लेके आता हूं, इफ आई टेक C2 इनटू कंसिडरेशन, तो C2 कार्बन एंड कार्बन इन दोनों के बीच में भी दो ही बॉन्ड बनते हैं, एंड यहां पे आप 2 electrons are involved over here, and therefore 4 electrons are left out. 1 2, इसको इस तरह से दिखा दो. One, two, three, four. 1 2 3 4. आपने इस तरह से कुछ दिखा दिया. So when you show it like this, and these are two bonds, it makes us think that these two bonds are one sigma and one pi, because valence bond theory tells us that whenever there are two bonds, I will consider one as sigma and one as pi. One will be formed due to head-on overlap, and one will be formed due to lateral overlap. That is the logic which valence bond theory uses. बट अगर आपने सेम लॉजिक यहां पे लगाया तो आपसे भारी बलंडर हो जाएगा. ओके, सो दिस इन फैक्ट कंटेन्स दीज टू बॉन्ड्स आर इन फैक्ट टू पाई बॉन्ड्स. नाइदर ऑफ देम आर सिग्मा बॉन्ड्स, बोथ ऑफ देम आर पाई बॉन्ड्स. अभी बोथ ऑफ देम आर पाई बॉन्ड्स, ये कैसे हमें पता चले कि बोथ ऑफ देम पाई बॉन्ड्स ही हैं? ओके, सो इसका एक्सप्लेनेशन मॉलिक्यूलर ऑर्बिटल थ्योरी से ही आता है. इज दैट अंडरस्टूड? एक और फीचर ये है कि a lot of people try to think that okay, there is a bond order. So since this topic is about molecular orbital theory, I would expect that थोड़ा आपको बैकग्राउंड आपको मालूम होना चाहिए. जैसे कि bond order determines the number of bonds which are present between two atoms. If it is a whole number like 1, that means the number of bonds between two atoms will be 1. If if it is 2, then if the bond order is 2, then the number of bonds between two atoms is also 2. तो अगर आपने किसी मॉलिक्यूल को देखा और उस मॉलिक्यूल में उस एटम ने किसी और एटम के साथ एक बॉन्ड बनाया है, तो वो बॉन्ड का बॉन्ड ऑर्डर 1 हो जाएगा. ओके, फॉर एग्जाम्पल अगर मैंने HCl ले लिया एंड मैंने आपसे पूछा कि बताओ इसका बॉन्ड ऑर्डर क्या है, तो आप बोलोगे बॉन्ड ऑर्डर 1 बिकॉज देयर इज वन बॉन्ड. बट इफ आई टेक समथिंग लाइक दिस डबल बॉन्ड, सो यू विल से दैट द बॉन्ड ऑर्डर ओवर हियर इज 2. बॉन्ड ऑर्डर एवरेज नहीं होता है, बॉन्ड ऑर्डर एवरेज कुछ और चीजों में होता है, बट यहाँ पे नहीं. यहाँ पे हम इंडिविजुअल बॉन्ड्स को लेके चलते हैं. सो दिस CC bond is having a bond order of 2. Similarly, over here also the bond order is 2. But even though the bond order is 2, the bonds are 1 sigma and 1 pi in case of CH2, but in case of C2, it is just 2 pi bonds. Okay? नेक्स्ट इज द 14 इलेक्ट्रॉन सिस्टम. हाईली मतलब इसमें काफी कुछ मिसकंसेप्शन भी है. एक नॉर्मल सा आइडिया होता है विच इज लाइक, आई थिंक यू माइट हैव हर्ड समवेयर एज वेल, दैट इफ आई टेक एनी एंटिटी, डायटोमिक स्पीशीज ले लेते हैं, जैसे कि N2 ले लिया हमने. ओके, मान लो N2 ले लिया, और if I take O2, 2 plus, okay, C2, 2 minus, all of these have 14 electrons. All of these have 14 electrons. Generic idea ये, lot of people say 14 इलेक्ट्रॉन्स मतलब बॉन्ड ऑर्डर 3, बॉन्ड ऑर्डर बिकम्स 3। बहुत लोगों ने देखा है, बहुत लोगों ने सुना भी होगा, बहुत लोगों ने पढ़ा भी होगा, बहुत लोगों को बताया भी गया होगा कि बॉन्ड ऑर्डर 3 हो जाता है। इफ देयर इज 14 इलेक्ट्रॉन सिस्टम, बॉन्ड ऑर्डर बिकम्स 3। ये चीज को एक्सट्रापोलेट कर देते हैं लोग हेटेरोन्यूक्लियर डायटोमिक स्पीशीज में, जैसे कार्बन मोनोऑक्साइड, उसका बॉन्ड ऑर्डर 3। हम आगे चल के पढ़ेंगे कि उसका बॉन्ड ऑर्डर अप्रोक्सीमेटली हम लोग 3 लेते हैं, लेकिन इट्स एक्चुअली नॉट 3। ओके, बट लेट चलो ठीक है, मान भी लेते हैं कि कार्बन मोनोऑक्साइड में बॉन्ड ऑर्डर 3 है। अगर यही कंसेप्ट को इफ आई एक्सट्रापोलेट टू BF, boron has 5 electrons and fluorine has 9 electrons, so there are 14 electrons। ये 14 electrons के कारण जो बॉन्ड ऑर्डर अगर आप ये बोल दिए कि 3 होगा, तो there will be a huge mistake। okay, there will be a huge mistake। the bond order over here is 1। okay, so such extrapolations about electron systems is something which is a very crude knowledge, and that does not help you understand things properly। वैलेंस बॉन्ड थ्योरी और मॉलिक्यूलर ऑर्बिटल थ्योरी में एक और चीज का डिफरेंस मैं आपको बता देता हूं कि वैलेंस बॉन्ड थ्योरी में ये बोला गया कि वैलेंस शेल will affect the bonding behavior। whatever bonds are formed are due to the valence shell electrons। चलो ठीक है, लेकिन मॉलिक्यूलर ऑर्बिटल थ्योरी ये कहता है कि फाइन, valence shell might be having a greater influence, but it is not true that other electrons which are not the valence shell electron will not influence the nature of this molecule। for example, in this carbon, this becomes the valence shell, and according to valence bond theory और valence shell electron pair repulsion theory, उनके हिसाब से सिर्फ यही डिटरमाइन करेगा कार्बन के मॉलिक्यूल्स जो भी बनते हैं उनकी सारी प्रॉपर्टीज। बट ऐसा नहीं होता है, जो भी दूसरे इलेक्ट्रॉन्स हैं दे विल ऑल्सो अफेक्ट द नेचर ऑफ दिस any chemical species which is created। and molecular orbital theory says that ये जितने electrons हैं, whatever be the number of electrons, all of them will affect। मान लो कि 4 electrons है, 5 electrons, 6 electrons, अगर एक molecule बना है और 14 electrons है, तो ये 14 के 14 electrons molecule के कुछ properties को determine करने के लिए they will influence it। it's not that you can just take the valence electrons and present a theory। okay, molecular orbital theory says that man, you have to take all the electrons which are coming in the picture। दूसरे electrons ने गलती क्या की है? okay, so this is the first issue, and I've explained you the second one। a lot of I would say trick shots which are utilized in a number of places, but they do not work in a number of cases। so to understand how do things work, you need to understand the basics। let's move on to the next part। molecular orbital theory 3 चीजों पर टिकी हुई है। okay, it's a chair or it's like a tripod। tripod देखा होगा आपने, tripod में 3 legs होते हैं, 3 चीजों पर रेस्ट करती है, और इन तीनों चीजों को समझना काफी इंपॉर्टेंट है। फर्स्ट थिंग इज मिक्सिंग ऑफ एटॉमिक ऑर्बिटल्स। ये मिक्सिंग द वर्ड है, ये अपने हाइब्रिडाइजेशन में भी आपने इनकाउंटर किया है। we'll see next key what is the difference between this mixing and the mixing that you have seen in hybridization। so first is mixing of atomic orbitals। ये mixing का मतलब क्या है? okay, what are we mixing? हम बना क्या रहे हैं मिक्स करके? second, molecular orbital diagram। ये डायग्राम किस चीज का डायग्राम है? ये डायग्राम हम बनाते क्यों हैं, और what are we trying to suggest using this diagram? and third, how to fill electrons in these diagrams। so if you have understood the first part, that is mixing, then the second part will become easy। if you have understood the second part, third part is just an extension of Bow principle, Hund's rule, Pauli exclusion principle। ये सारे principles मिलके third rule को आपको समझने में हेल्प करेंगे, जो कि इट्स नॉट वेरी कॉम्प्लिकेटेड. सो आउट ऑफ ऑल दीज 3 pillars of molecular orbital theory, the first 2 are very important, that how mixing takes place and how do we construct molecular orbital diagram. So we start करते हैं मिक्सिंग से. मिक्सिंग 2 तरह की होती है. एक होता है इंट्रा ऑर्बिटल मिक्सिंग, सॉरी नॉट इंट्रा ऑर्बिटल, इंट्रा एटॉमिक मिक्सिंग, एंड वन इज इंटर एटॉमिक मिक्सिंग. फॉर एग्जाम्पल, when you had taken the case of CH4, in this, to prepare CH4, you had suggested that carbon whose configuration is 1s2, 2s2, 2p2 undergoes a change to 1s2, 2s1, 2p3, and then you had mixed these 2 set of orbitals. ओके, आपने क्या किया, यहाँ पे S2s was mixed with 2p. This is what you did. Okay, this is what you did. This is known as a intra-atomic. ये जो मिक्सिंग हो रही है, इसमें हाइड्रोजन का कोई इन्वॉल्वमेंट नहीं है. इस मिक्सिंग को हम हाइब्रिडाइजेशन बोलते हैं. This mixing is called hybridization. So intra-atomic mixing of atomic orbitals is known as hybridization. Okay, you already know this. In case of hybridization, एक बहुत ही इंटरेस्टिंग चीज आपको समझनी होगी. In case of hybridization, अब देखो, जैसे आपने ये कंपाउंड बनाया था, फॉर एग्जाम्पल SF6. ओके, सो SF6 का हाइब्रिडाइजेशन आप क्या बोलते हो, sp. सो सल्फर is 6, fluorine, sulfur has 6 electrons in valence shell, 6 bonds are formed with fluorine. So you will say that the hybridization is sp3d2. आप सोचो, समझने की कोशिश करो कि आपने सल्फर के 3s, सल्फर के 3p और सल्फर के 3d ऑर्बिटल सबको मिक्स कर दिया. ओके, जब ये इंटर एटॉमिक मिक्सिंग होती है ना, तो ऐसा थोड़ी है कि 3s एंड 3p एंड 3d इनकी एनर्जी सेम है. इनकी इज देयर, डू दे हैव सेम एनर्जीज? 3s, 3p, 3d, डू दे हैव सेम एनर्जीज? नो, दे डू नॉट हैव सेम एनर्जीज, येट यू मिक्स देम. सो इंट्रा एटॉमिक मिक्सिंग when it takes place, then even though the atomic orbitals have different energies, they mix to create orbitals of equal energies. Okay, even though the energies of these orbitals are different, you can mix them. What is interatomic mixing of atomic orbitals? Interatomic mixing is what we study as linear combination of atomic orbitals. In an interatomic mixing, 2 atoms will allow their atomic orbitals to mix with each other. Okay, so यहाँ पे 2 न्यूक्लियस रहते हैं. इस तरह से मान लो कि एक p ऑर्बिटल है प्लस माइनस, so 2 different atoms will allow their orbitals to mix. These can mix with each other. You have to remember that this mixing requires AOs to be of alike or similar energies. In this case, a huge energy difference cannot allow mixing to take place. इंट्रा एटॉमिक में ये हो जा रहा था, लेकिन यहां पे बेटा नहीं होगा. या तो इन दो ऑर्बिटल्स जो कि मिक्स हो रहे हैं, इनकी एनर्जी सेम होनी चाहिए, या फिर बहुत ज्यादा डिफरेंस नहीं है, थोड़ा डिफरेंस होने से हो जाएगा, बट इफ द डिफरेंस इज ह्यूज देन दे विल नॉट मिक्स विद ईच अदर. इज दैट क्लियर? सो इंटर एटॉमिक involves two nuclei, and therefore the mixing is of atomic orbitals which have almost equal or alike energies. But intra-atomic atomic orbitals of different energies can mix with each other to generate orbitals of alike energies, or orbitals of equal energies. So ये इंटर एटॉमिक को ही हम पढ़ेंगे लीनियर कॉम्बिनेशन ऑफ एटॉमिक ऑर्बिटल्स में. ओके, सो लेट्स मूव अहेड. व्हाट इज लीनियर कॉम्बिनेशन? लीनियर कॉम्बिनेशन, सिंपल आइडिया, लीनियर कॉम्बिनेशन का मतलब एडिशन या सब्ट्रैक्शन. ओके, लीनियर कॉम्बिनेशन मींस आइदर एडिशन और सब्ट्रैक्शन. ओके, लीनियर combination means addition or subtraction. अब ऐड किसको कर रहे हो और सब्ट्रैक्ट किसको कर रहे हो? ओके, आपको यह समझना होगा कि लीनियर कॉम्बिनेशन, दिस मॉलिक्यूलर ऑर्बिटल थ्योरी is derived from the quantum mechanical model. And in the quantum mechanical model, we consider an orbital to behave as a wave. अब ये wave, whenever we consider a wave, so this wave is like this. Okay, just draw it a little better. Just a moment. Okay. So this is a wave, and this wave is going to combine with another wave. When waves combine with each other, the process is known as interference. Think of it in this way, that there is a pond and you are standing at the bank of the pond. ठीक है? आप क्या कर रहे हो कि एक stone लेके you are throwing it in the middle of the pond. What you will see that the waves or ripples will start originating from where the stone hits the water, and they'll move towards the bank. If you throw another stone exactly at that point, some new waves will be created and these waves will combine with each other. जैसे समंदर में लहरें combine करके एक bigger wave बनाती हैं, ऐसा होगा. But if you throw a stone somewhere between the original point where the stone hit and the bank, then the waves, you will find certain waves moving in opposite directions, and that will cause something known as a destructive interference. This destructive interference will be a cancellation effect, and इसके कारण होता क्या है, ये जो wave आप देख रहे हो, तो ये सारी इधर जो amplitude है, this amplitude decreases. ये जो amplitude है, this amplitude decreases. So considers orbital as wave functions. Interference of waves results in mixing, and interference can construct it. So I've shown this over here. Suppose this is wave 1 and wave 2. You can see that they are very properly aligned. If you look at wave 1, this is the crest, this is the crest, this is the crest, this is the crest, this is the trough, this is the trough. So all of the points along wave 1, along this path, along this path, all of them are very neatly aligned with wave 2. When they combine with each other, तो एक additive effect होता है, and the net amplitude increases. However, if the alignment is bad, you can see along this part, along this line, or along this line, wherever we have crest, over here we have trough. Okay, so if we have a crest, we have a trough. we have a trough, we have a crest. So with this idea, you can see that if this interference takes place, what we will have is a nullification. Okay, we will have a destructive interference, or which will be called a nullification. ठीक है, कैंसिल हो जाएंगे. इसको थोड़ा हम मैथमेटिकली अगर समझने की कोशिश करें तो ये देख सकते हैं कि अगर आपने 1s ऑर्बिटल का साई वर्सेस डिस्टेंस प्लॉट किया, आई होप यू रिमेंबर द साई वर्सेस डिस्टेंस प्लॉट फॉर 1s इज लाइक दिस. ओके, एंड दीज आर टू न्यूक्लियाई. These are two nuclei. So when they overlap, okay, when there is an additive effect, what will happen is we will get a plot like this. What does this plot tell us? See, psi does not have a real meaning, but psi square does. So if I take the square of this, yeah, this will increase even more. And this will go like this. Okay, this is psi square versus r plot. It means the probable, and psi square gives what? Probability density, which means the probability of finding electrons between the two nucleus or two nuclei has increased. This probabilities, the density of these probabilities has increased between the two nuclei. Okay, so this is constructive interference. ये constructive interference होता है. But इसी के जगह अगर मैंने destructive interference लिया, तो when this happens and we get something like this combines and we get something like this, and we take the psi square versus r plot, so you have to understand that if I take psi square, then this part will go up. This part will go up because this is psi. So if I take psi square, whatever is shown downward will go up. Okay, so and if this goes up, we will get a plot like this. See, in this region and this region, whatever this region is and this region, these two regions are unaffected, but the regions in which the destructive interference has occurred, that is this one and this one, we can see that the electron density looks like it is lesser than the one which is outside. मतलब इसको मैं अगर ये जो स्टिक मार्क्ड है इनको मैं आउटसाइड वाले रीजन बोल दूं, तो आउटसाइड वाले रीजन में मुझे दिख रहा है कि थोड़ी ज्यादा इलेक्ट्रॉन डेंसिटी है, बट over here we have less. And so this is psi square versus r plot, and this is for destructive interference. Destructive interference generates anti-bonding molecular orbitals. Okay, it generates anti-bonding molecular orbitals. Sorry guys. So if I represent one wave as psi1, another wave as psi2, and इसका मैं स्क्वायर कर देता हूं, then I will get psi1 square psi2 square plus 2 psi1 psi2. But if it is a difference, so you can see very clearly that this is what constructive interference looks like. Constructive interference has this part added, so psi1 square and psi2 square, this part is common, and this part it increases by this extent, so the probability density between the two nuclei increases, whereas the probability density between the two nuclei decreases by 2 psi1 psi2. Okay, so I said that it forms antibonding molecular orbitals. Now somebody if wants to know that why, तो उसको समझते हैं इस तरह से. पिछले वाले केस में आप ये देख रहे हो कि ये दो न्यूक्लियस के बीच में इलेक्ट्रॉन डेंसिटी इंक्रीज कर रही है. प्रोबेबिलिटी डेंसिटी इंक्रीज करने का मतलब इलेक्ट्रॉन डेंसिटी इंक्रीजेस. So if between two nuclei electron density increases, then can we say that there will be greater attraction as compared to earlier? पहले जितना था, पहले जो थोड़ा मोड़ा इलेक्ट्रॉन अट्रैक्शन था, now it has increased. So attraction increases. और किसके अट्रैक्शन इंक्रीज करेंगे? न्यूक्लियस का इलेक्ट्रॉन की तरफ. Attraction increases. Always remember, whenever attraction increases, or when attraction takes place, the extent of attraction increase, attraction takes place, then energy will be released. So this will cause release of energy. This will cause release of energy. So if energy is released, then with respect to the original orbitals, ये जो situation बन के आ रहा है, और whatever this constructive interference is generating, whatever this linear combination is generating, that will have lesser energy than these two. Can I say that? With respect to the energy of 1s, the energy of the sigma 1s is lesser. Why? Because there is an attraction. An attraction has taken place because the electron density between the two nuclei has increased, and we have proved that why it has increased, because the probability density increases. If we extrapolate the same idea to एंटी बॉन्डिंग, तो आप देखो कि पहले के कंपैरिजन में अभी जो प्रोबेबिलिटी डेंसिटी है, दैट हैज decreased, guys. Can you see that? That has decreased. So if this decreases, that means attraction, attraction decreases, and if attraction decreases, then why would attraction decrease? अट्रैक्शन डिक्रीज होने का मतलब न्यूक्लियस न्यूक्लियस के बीच में रिपल्शन इंक्रीज हो गया. Repulsion between nuclei increases, and whenever repulsion takes place or when repulsion increases, energy is absorbed, energy is increased. So the energy of this combined atomic orbit combined set of atomic orbitals, whatever you have created, I'm still not calling it molecular orbitals, let's say I call it combined set of atomic orbitals, that has higher energy than what it was earlier for 1s and 1s. Is that understood? So this has higher energy. This set has higher energy. So if I were to construct, ये आप इसीलिए बोलते थे ना कि यहां पे अगर आपने 1s बनाया और यहां पे आपने 1s बनाया तो एंटी बॉन्डिंग की एनर्जी आप ज्यादा दिखाते थे एंड बॉन्डिंग की एनर्जी आप कम दिखाते थे. ओके, एंड दिस इज व्हाई द एनर्जी increases for anti-bonding and energy decreases for bonding. Is that clear? I hope you have understood this. ठीक है, चलो आगे बढ़ते हैं. एक चीज आप समझ लो कि ये जो चीज जनरेट की है आपने, ये अब एटॉमिक ऑर्बिटल्स रहे नहीं है. दे आर नो लॉन्गर एटॉमिक ऑर्बिटल्स. व्हाट दे हैव बिकम इज अ मॉलिक्यूलर ऑर्बिटल, क्योंकि दो हाइड्रोजन आके they have mixed with, they have made their atomic orbitals mix, and the new thing whatever is created is like a baked thing. केक बनाने के लिए आपने बहुत सारे इंग्रेडिएंट्स डाले, तो जो बन के आता है उसमें इंग्रेडिएंट्स का आपको फ्लेवर पता चल सकता है, लेकिन वो इंग्रेडिएंट्स आपको दिखते नहीं है. सो यू नो लॉन्गर सी द एटॉमिक ऑर्बिटल्स, व्हाट यू आर सीइंग इज अ मॉलिक्यूलर ऑर्बिटल. ओके, सो ये लीनियर combination of atomic orbitals जो अभी भी हम we are continuing with this linear combination of atomic orbitals किस तरीके से होते हैं. तो linear combination ना can take place by head on mixing, head on overlap से. okay, two orbitals are coming and they are performing a head on overlap. okay, this is head on, this is head on. This is head on. Okay, whenever head on overlap or head on mixing takes place, you will always get a sigma bond. You'll always get a sigma bond or sigma molecular orbital. तो जितने भी orbitals हैं, देखो, you do not have to remember कि which orbitals will give rise to head on overlap, which orbitals will give rise to lateral overlap. What you have to remember is how they are overlapping. Suppose this is px and this is px and this is the x-axis, this is the x-axis. px and px are approaching each other along the x-axis, that will always be head-on overlap. ठीक है, that will always be head-on overlap. But suppose px, this is px, it approaches another px along y-axis. Then what you would have is a lateral overlap. So in examination they will not ask you that what, so this is lateral overlap that will take place. So जब lateral overlap और sideways mixing होती है, then you get pi molecular orbital, delta molecular orbital and phi molecular orbital. इस delta and phi होते क्या है? So remember that pi molecular orbital involves two lobes at one nuclei mixed with two lobes at another nuclei. Okay, or you can say 4 lobes are laterally coming towards each other. That is pi. Delta is when 4 lobes at one nuclei laterally overlap with 4 lobes at another nuclei. For example, something like this. A lot of people have this confusion that whenever d orbitals overlap with d orbitals, it will always create delta bond. No, delta bonds are created only when a orbital overlap takes place, two atomic orbital overlap takes place, where 4 lobes laterally overlap with all the 4 lobes. ठीक है, तो डेल्टा बनता है. So this is where delta is created. Okay, मान लेते हैं ये x और ये y है, and this is x and this is y and this is along z axis. This overlap is taking place. You can see that there are 4 lobes which are overlapping with each other. 1, 2, 3, 4. And this one is phi. Phi happens when 6 lobes at one nuclei simultaneously overlap with 6 lobes, or laterally overlap with 6 lobes at another nuclei. और ये हम सिर्फ f orbital में देखते हैं. Okay, we observe this in f orbital. Non-effective mixing क्या होती है? Non-effective mixing तब होगी when the extent of positive overlap and extent of negative overlap is exactly the same. For example, I have a py orbital and a px orbital which is trying to overlap. ये x axis है, ये px orbital है. अगर इनका overlap हुआ तो this part and this part will have a same symmetry. You can see that plus and plus इनका overlap same symmetry में होगा, इनका नहीं होगा. So this will be opposite symmetries, and that will create a non-bonding situation. Okay, non-bonding situation can be created like this. Understood? So over here I have given a picture of how many ways we can create head-on overlap. देखिए कितने सारी जगह पे मैंने head-on overlap करवाए हैं. SS head-on, SS. So I have shown that how bonding molecular orbitals are created and how anti-bonding molecular orbitals are created. So this is bonding molecular orbital and this is anti-bonding. One thing you have to remember, that if the symmetries are alike, plus and plus has to do with the symmetries. If the symmetries are alike, then it will be bonding, and if they are non-alike, then it will be anti-bonding. Is that clear? If they are non-alike, that will be anti-bonding. Because it is anti-bonding, you can see a nodal plane between the two nuclei, which suggests that the electron density between the two nuclei is 0. And therefore, presence of a nodal plane causes or shows that this has a higher energy compared to a bonding molecular orbital. So this को हम bonding molecular orbital बोल देंगे, and this will be called ABMO. Okay. The same goes over here. Bonding sigma px and sigma star px. This is sigma This is px overlapping with s, so sigma spx. This is dx square minus y square overlapping head on with another dx square minus y square orbital. Now you have to understand one very important idea, that how many nodal planes should I be counting? Okay, so nodal planes of molecular orbital, जैसे nodal plane of atomic orbitals, any plane which was going through the nuclei, we were counting it as a nodal plane for that given atomic orbital. Okay, for nodal plane for molecular orbital, nodal planes for molecular orbital. Nodal planes for molecular orbital will be counted in this way. So those planes which satisfy this condition will be included. They should go through the internuclear region. They should go through the internuclear region. Okay? So if I draw one plane like this and one plane like this, they will not be called a nodal plane because that is not going through the internuclear region. So between the two nuclei, दो न्यूक्लियाई के बीच के जो प्लेन बनाएंगे वो होगा नोडल प्लेन. So this is a nodal plane, and if you are being asked that sigma star px will have how many nodal planes, you will say that there is only one nodal plane, because then this one and this one, they though are going from the nuclei, but they are not present in the between the internuclear region. Okay, they should go through the internuclear region. These are the pi molecular and pi molecular orbitals. These pi molecular orbitals are bonding molecular orbitals and pi anti-bonding. You can see that there is plus over here. This is plus plus minus minus, that is overlapping, and over here plus minus minus plus, that is causing a anti-bonding pi anti-bonding to be formed. Please do remember the shapes of these pi anti-bonding and pi bonding, क्योंकि इनके shapes से आगे हम organic chemistry के काफी molecular orbital behaviors को explain करते हैं. Okay? जैसे एल्डिहाइड कीटोन्स में किस एंगल पे अटैक होगा, ये एक्सप्लेन करने के लिए I need to use this picture. This is a nodal plane, this is a nodal plane, this is a nodal plane. Now you can say that why is this considered as a nodal plane? Because it is this is also the internuclear region. Okay, so this is going through the internuclear region, this is also going through the internuclear region. So therefore this will be called a nodal plane. Okay, this will be called a nodal plane. But यहाँ पे आप एक चीज देख रहे हो, यहाँ पे बहुत जगह पे G लगा के रखा गया है, U लगा के रखा गया है. In previous case as well, G is written, U is written, G is written, G is written. What is the meaning of this G and what is the meaning of this U? The meaning of this G and U can be understood if we learn what is known as gerade and what is known as ungerade. जेरेड और अनजेरेड का मतलब ये होता है कि अगर किसी एक ऑर्बिटल में सेंटर ऑफ सिमेट्री है, then it will be called gerade, and if something does not have a center of symmetry, then it will be called ungerade. For example, I take this p orbital. इसको चेक कैसे करते हैं? देखो, चेक करने का मैं तरीका आपको बताता हूं. So how do we check gerade and ungerade? This is a p orbital. Let's say px. This is plus, this is minus. ये पिक्चर आपको दिख रहा है? प्लस राइट की तरफ है, माइनस लेफ्ट की तरफ है। सबसे पहले आपको करना क्या है, you rotate first thing is you rotate the orbital on the axis on which it is present, okay, or you rotate it on the axis or about the axis on which it is present। तो इसको जब रोटेट करोगे तो आपको तो फिर से यही मिल जाएगा ना बेटा, this is plus minus। now you have to, and ये रोटेशन कितने से करना है, 180 डिग्रीज रोटेशन। then you have to rotate it at an axis perpendicular to the previous one। if you are taking this as the axis along which you are rotating, then you take another axis which is perpendicular to the previous one, orthogonal to the previous one, and उसके about आप rotate कीजिए by 180 degrees, okay, rotate by 180 degrees। so what you will get is this picture। जो प्लस है वो दूसरी तरफ आ जाएगा और माइनस है वो इस तरफ आ जाएगा। Is the picture the same as the original one? No, because the plus was on the right and the minus was on the left. In this case, plus is on the left and minus is on the right. Therefore, if the pictures are different by doing this operation, rotation about the axis, first is rotation about the axis on which the orbital is present, and then along an axis which is perpendicular to it. If the appearances are different, then it is called ungerade. It is called ungerade। मैं आपको एक जेरेड ऑर्बिटल दिखाता हूं। This is pi star। rotate it along this axis by 180 degrees, you will be getting something like this। sorry, you'll get something like this, minus, plus, something like this, and then you take an axis perpendicular to the previous one। ये जो axis लिया था इसका perpendicular एक axis ले लो and rotate it by 180 degrees। pardon my diagrams, okay। are we getting the same appearance as the previous one? बताओ, ये जो appearance है जिसमें कि प्लस यहाँ, माइनस यहाँ, माइनस यहाँ, प्लस यहाँ, are we getting the same appearance? yes। so ये जो ऑर्बिटल है वो जेरेड है। so try and understand, इन सारे ऑर्बिटल्स में आप खुद से सेम एनालिसिस कर सकते हो, जैसे कि ये अनजेरेड लिखा गया है, ये जेरेड लिखा गया है, this is written as gerade, this is written as gerade। so please try and understand if it is written in whatever it is given, you can do an analysis once again for all of them and let me know in the comment section that where you were able to do that, okay। so ये एनालिसिस होता है जेरेड और अनजेरेड का। क्यों हमें इसकी जरूरत है? क्योंकि आगे चल के जब हम मॉलिक्यूलर ऑर्बिटल डायग्राम्स क्रिएट करने की कोशिश करेंगे, देन वी विल लर्न दैट व्हेन वी मिक्स ऑर्बिटल्स, वहां पे भी मिक्सिंग हम फिर से पढ़ेंगे, व्हेन वी मिक्स ऑर्बिटल्स दिस मिक्सिंग रिक्वायर्स प्रॉपर सिमेट्री। सो जेरेड एंड अनजेरेड आर अ मेजर ऑफ सिमेट्री। gerade orbitals or gerade molecular orbitals overlap with gerade molecular orbitals, and ungerade molecular orbitals overlap with ungerade molecular orbitals. But that will come later. We'll discuss that later. But please do keep this thing in mind. Okay, so next is molecular orbital diagram. तो molecular orbital diagram हम लोग जो बनाते हैं, ये हम लोग दो तरह के molecules के लिए बनाते हैं. ये एक तो बनाया जाता है होमोन्यूक्लियर डायटोमिक मॉलिक्यूल, जैसे कि H2, B2, C2, N2, O2, F2, इन सब के लिए बना दिया गया. And then we make it for heteronuclear diatomic molecule. Now heteronuclear diatomic molecule में दोनों atoms different होंगे. Okay, चार्ज हो सकता है प्रेजेंट हो, नहीं भी प्रेजेंट हो सकता है, बट देयर आर 3 subsections. One is without sp mixing in both. इसका एग्जाम्पल मैं ले लेता हूं HF. With sp mixing in one of the atoms, that is CO. ये काफी important. With sp mixing in both the atoms, that is Cn minus. अब ये sp mixing होती क्या है? ओके, इतने सारे मिक्सिंग तो हमने देख ली. sp मिक्सिंग अब होती क्या है? प्लीज ट्राई एंड अंडरस्टैंड कि इन तीनों के जो हम लोग जनरली बुक्स में जिस तरीके से मॉलिक्यूलर ऑर्बिटल डायग्राम दिया रहता है, द वे इट इज जनरली रिप्रेजेंटेड, दे ड्रॉ हेटेरोन्यूक्लियर मॉलिक्यूलर डायटोमिक मॉलिक्यूल्स. Molecular orbital diagram for everything is being shown exactly alike, like for HF, CO, Cn minus, everything is shown alike. ऐसा नहीं है. There is a huge difference because in certain atoms sp mixing takes place, in certain atoms sp mixing does not take place. So sp, what is sp mixing? What is this feature? So sp mixing is a atomic feature. Okay, sp mixing is a atomic feature. Let's try and understand. We take certain elements from this set. I ask you to take boron, carbon, nitrogen, oxygen and fluorine. These are documented values of ऑर्बिटल आयोनाइजेशन एनर्जी. इन ऑर्बिटल से अगर मुझे इलेक्ट्रॉन्स को निकालने हैं, then how much energy needs to be given? This is a chart of that. So you can see that these energy values are being given, and if you look at for boron, then in case of boron, the energy difference between 2s and 2p. So 2s and 2p energy difference is about so this is 14 and this is 8.3. So we have energy delta E as about how much? 86. So 5.7 electron volts. In case of carbon, we have 19.5 and 10.7. So very close to about 9. Very close to 9. I'm taking very approximately to 9 electron volts. Nitrogen, the energy difference between these two is 25.5 and 13.1. So it is about 12 इलेक्ट्रॉन वोल्ट. ये जो एनर्जी डिफरेंस है, ये 2s ऑर्बिटल एंड 2p ऑर्बिटल के बीच का एनर्जी डिफरेंस है. जब आप जैसे ही ऑक्सीजन पे जाते हैं तो आप देख रहे हो कि 16 है, ये अबाउट 16 इलेक्ट्रॉन वोल्ट्स का डिफरेंस हो गया. एंड यहां पर उससे भी ज्यादा 18, अबाउट 19 एंड 46. सो about 25 electron volts. So the energy gap between 2s and 2p orbitals is increasing as we move along the second period. So boron से लेके boron, carbon, nitrogen, oxygen, fluorine, यहाँ पे 2s and 2p का गैप इस तरह से था, तो यहाँ पे इस तरह का था. Over here it is like this, over here it is even more, and this is very large. So it is what actually happens when you construct this molecular orbital diagram. I have told you that atomic orbitals have to overlap, linear combination has to take place. So s orbital will of one atom will try to overlap with s orbital of another atom, but it is quite possible that before they overlap with each other, before atomic orbitals of two atoms overlap with each other, the atomic orbitals within one atom can undergo mixing because the energy difference is less. मतलब before inter-atomic mixing, intra-atomic mixing takes place. This intra-atomic mixing takes place in boron, carbon, nitrogen. A lot of people think that it will take place in all 14 electron system. ऐसा नहीं है. It will take place, it is an atomic feature. Okay, it's an atomic feature that it will take place in boron, carbon, nitrogen. Is that clear? Now, ऐसा भी नहीं है कि सिर्फ इनमें होता है, दूसरे जगह भी होता है. Let's try and understand. So if I take फ्लोरीन तो हमने ले लिया, चलो उठाते हैं क्लोरीन को भाई साहब को. If I take chlorine, then bromine. If you look at chlorine, then it is 14 and 25, about 11 electron volts. 24 and 12.5 less, about somewhere close to, again the same, close to 11 electron volts, close to 11 electron volts. As we go to iodine, ये जो एनर्जी गैप है और कम हो जाती है, तो फ्लोरीन में जो एनर्जी गैप है दैट इज द लार्जेस्ट, क्लोरीन इज लेसर, ब्रोमीन is even lesser, and iodine is the least. What is the implication of this? You must have read that among all these halogens, chlorine, bromine, iodine, they are colorless. Sorry, they are colored, and fluorine is colorless. ये colored दिखता है आपको. Why they are observed as colored? क्योंकि इनके जो atomic orbitals हैं ये इतने नजदीक हैं कि इनमें electronic transitions can take place easily. We will discuss this later in the application of molecular orbital diagram, molecular orbital theory as well. But for now, I'm telling you, when we look at the behavior of molecules to display color, then lesser the energy gap, more chances of them to show the color in the visible region. If there is a larger energy gap, तो जो ट्रांजिशन होगा वो यूवी रीजन में मुझे उसकी कलर्स दिखेंगे. ओके, सो प्लीज रिमेंबर दैट now you can make sense of the fact that why did I say that HF is without mixing, because H does not undergo mixing of 2s and 2p. अब 2s 2p तो है ही नहीं, फ्लोरीन में तो होता नहीं है. therefore this is an example of a molecule which does not have sp mixing. CO is an example where one of them has sp mixing, the another one does not have, while this one is the one where both of them have sp mixing. So our objective would be to draw and to learn how to draw the molecular orbital diagrams for these, and to investigate what would the molecular orbital diagrams for these two would look like. Okay, so that's all for today, guys. This is the first part of the molecular orbital theory that I have discussed. Please do remember that हम इसके बाद एक और लेक्चर लेंगे जिसमें कि हम डिस्कस करेंगे कि HF का, CO का, CN माइनस का molecular orbital diagram हम बनाते कैसे हैं. And इसको डिस्कस जब हम करेंगे, then we will see a lot of things which are different or which appear as slight aberrations from what we usually know. Okay, so as usual, told you that if you are a 12th standard student who is appearing for JEE, please do check out the Vedantu Eklavya program. And if you are in 11th standard, 12th standard, right, and promote 12th standard, then also please do check out the Vedantu Eklavya program. It's one of the best programs in the country which can help you achieve the score and the rank that you want. Also, there are some important links given in the description. The first thing is the JEE Topper Notice Board. Please do remember that for whatever notices that we give out for multiple entry points and new programs that we are going to launch and any open tests that we want to give, this is where we'll put on the information. Also, any information related to Eklavya will be put on this Telegram channel, that is Vedantu JEE Eklavya 2022. JEE 2023 aspirants, please do navigate to this to understand what are the programs which we offer and what are the ways you can enter Vedantu to enrich your subject knowledge. And JEE 2024 aspirants जो कि अभी 11th में हैं और next year अपना JEE advance देंगे, please keep checking our videos regularly so that you would be at par with the best students in the country. Also, please do check all the information which comes on vdnt.in/JEE aspirant 2024. And the V Impact channel is a repository of PYQs and some interesting questions which is available nowhere. Please do check it out periodically to enrich yourself and your knowledge of all three subjects of physics, chemistry, maths. Even for biology, you can check it. Okay. And so with that, I take leave. It was lovely meeting with you once again, and let's meet each other in the next session of molecular vital theory. So bye guys, have a lovely time, be safe.